We move on to the next presentation, number 543. Evaluation of bending fatigue strength in automotive gear steel subjected to shot peening techniques.
So I'm going to talk to you today about the evaluation of bending fatigue strength in automotive gear steels subject to shot peening techniques. I'm Robert Lambert. I'm from Design Unit at Newcastle University. So a quick overview of what we're going to talk about today. I'll give you a bit of background to Design Unit, to know what the work we do and the project under which this work was undertaken. We'll then give some background as to why we were interested in this work. So we'll talk about a few different gear failure modes, and we'll talk a little bit about shot peening, and I'll then cover the test method that we used for the bending fatigue tests, and then we'll discuss the results, which will include looking at some residual stress profiles, some bending fatigue test failure, and we'll look at some fracture faces. So Design Unit, we're based in Newcastle University in England, established in the 1970s. We've got coming up on 50 years worth of experience in the mechanical power transmission and driveline design consultancy. We also operate the UK National Gear Metrology Lab, so we're responsible for traceability of gear measurements in the UK, and through that we're involved in transmission design, transmission testing, design of bespoke test fixtures, and training and input into international standards for gear design and analysis. So the project under which this work was completed is Ultran, so that's ultra lightweight transmissions and drivelines. That was an Innovate UK funded project, that's a UK government funded project. There were 9 partners, including 4 universities and 1 large automotive company. The project aim being to develop complementary lightweight technologies to deliver a step change in transmission and driveline weight. Obviously that's driven through this changing need to improve vehicle efficiency. We need to reduce emissions from vehicles. One of the best ways to do that is by reducing weight. So the total project value was about £5 million. I think £3 million of that was funded by Innovate UK. One of the deliverables of that was that we need to disseminate this information, so that's what this presentation is doing. We're spreading this test data out to the wider scientific community. So to give you a bit of background in gear design and failure, so we design and optimise gears to improve their performance and reduce the risk of failures occurring during their operation. So there's international standards that describe these kind of failures. I've got a couple of examples here. So we have contact fatigue. So this is driven by hertzian contact stresses. So as the gears come through contact, we have rolling sliding contacts come through. We have subsurface initiated cracks, which then lead to pitting at the surface, and this degenerates the efficiency of the gears. Bending fatigue failure, which I will cover a little bit more about in the next slide. But essentially here we have root-initiated cracks growing through the teeth, and we end up with detachment of the gear teeth. We have micropitting, which, if you believe most people, is a fatigue-based failure. Sometimes there's grey staining. We have very shallow surface-initiated cracks, and that's actually a failure that can arrest or lead into further failure modes, typically contact fatigue. And then we have more instantaneous failure modes, such as scuffing. This is just one example. Scuffing occurs when we have instantaneous breakdown of the lubrication film thicknesses. We end up with metal-metal contact of the 2 gear teeth, and because of the high sliding speeds, there's instantaneous welding and tearing. So yeah, these are instantaneous failure modes. And there are standards, I've listed some here, that describe how gear designers can look at how likely that to happen in operation. So to talk a little bit more about bending fatigue, since that's what we were testing for. So bending fatigue can be particularly catastrophic because you can get complete tooth detachment. That tooth is going to have to go somewhere, and typically that's going to go into the gear mesh, or it's going to go into associated drivetrain components such as bearings, which is very bad. The majority of bending failures initiate at the surface, for example at grain boundary oxidation, which is a problem that we see in gas carburized gears, or it might be near surface from inclusions from the steel making process. It can also be from geometric features such as grinding notches, but we do try to avoid those through manufacture. Because it's such a catastrophic failure mode, the safety factors are higher than in other failure modes. So therefore, you can see we've got a greater opportunity to reduce weight by increasing the bending fatigue strength. And just to quickly describe the actual failure mechanism, so essentially we treat the tooth as a small cantilever. We look at the load appearing at the highest point of signal-tooth contact, so when only one tooth pair is in contact, and we calculate the second moment variant at a 30-degree tangent plane where the tooth roots are, and if we've got the load coming in from the right-hand flank here, we'll see a tensile stress appearing in this tooth root here. The crack will then grow towards the neutral axis. That neutral axis is changing as the crack grows, and at the end it will then turn up towards the opposing tooth root and end up in complete tooth detachment. So the test method we use to evaluate the bending fatigue strength is we use a pulsator method, so this is a resonance test machine, and we use a staircase method for the test procedure. So the key thing about this machine is the design of the fixture that you can see down here, and we need to guarantee that the load is being transferred through the base circle of the gear, and that ensures that this is very applicable to what the gears actually see when in operation. We also make sure that we have this custom loading anvil, which makes sure that we're representing the line contact you would see during operation, and that we're not introducing load distributions which are predominantly towards one side, so we want it to be nice and even across the tooth. We use an endurance limit of 10 to the 7 cycles, and we can do that because these machines will operate at 150 hertz, so we can generate large number of cycles over a relatively small period of time. We use an R ratio of 0.05, and the gears themselves then were manufactured from a forged case carburizing steel, typical of the automotive industry, so you can see that here. Forged blanks and then manufactured using a standard process, and again that's making sure that what we're doing is typical of the actual application that these gears come from. So there's some gear data at the bottom there if anyone's interested in recreating these, and carburized using a commercial process, gas carburized these were. So shot peening, I'm sure everyone here knows about shot peening, but I will cover it anyway. So essentially we bombard the surface with accelerated media, which then indents the surface, we get some plastic deformation, and we then get compressive stresses induced under the surface. As we know, compressive residual stresses are good at helping to suppress crack initiation and crack growth. So clearly, as we know that the bending fatigue failures are near surface or surface initiated, this is a very good process for us to follow. ISO 6336, so the standard that describes contact fatigue and bending fatigue calculations, tells us that we can see suggested improvement between 0 and 10% in bending fatigue strength, depending on what quality of steel we're looking at. So of the processes we could choose, there's a number of different media you can look at. The processes that were selected for this particular package of work it was a proprietary condition cut wire process, so that's taking a section of wire, shearing off sections, and then treating them to create your somewhat spherical media. The other three processes were commercial processes using cast shot. The first being what the industry calls a typical process. The second being a slightly larger shot size, and this was chosen to be as closely representative of the condition cut wire process that we could go to. So I can't give you the details of the condition cut wire process, but the 330H process is close to that. It's an optimized process. We then looked at a fourth process, which was optimizing that further using a duplex shot peening method. So you use a larger shot to start with, which should induce compressive residual stresses deeper within the material, and then we use a smaller shot, which should give us nearer surface benefits. We did also then test, of course, baseline material as well, so you'll see the baseline data too. So the results for the compressive residual stresses. These colours don't seem to have turned up very well, but the red line across the top, that's our baseline material. We saw the greatest increase in the compressive residual stress for the condition cut wire process. So not only did we see the greatest residual stress at approximately minus 1,100 megapascals, we also saw the broadest peak across that range. The two standard single shot processes, so this is the S230H, this is the S330H. So as we'd expect, the larger shot size gives us improved compressive residual stress deeper in the material. Perhaps the surprising one here is the duplex method. you wouldn't expect to see a lower magnitude compared to the single process, the 330. You would expect the 330 shot size to give you a similar range, and the 110 to give you a closer surface improvement. But I think rather than showing that these are typical of that process, I think this tells us more about the process control and one of the problems that we see with shot peening with cast shot, and that is that you get a much larger distribution of shot size and shot hardness. So, for example, if we looked at the 230 shot size, within the shot that was used within that process, some of them will be 330 size and some of them will be 110 size. So I think that's a better reflection of that. And the results from the compressive residual stress are also reflected within the bending fatigue strength. So the red line again is the baseline steel. I should note the test method that you use for this type of testing gives you a 50% probability of failure. You can calculate the 1% probability of failure based on the standard deviation, which isn't in this table, but it is in the paper, so you should be able to find that there. Overall, we saw approximately it was an 86% uplift in bending fatigue strength for the condition cut wire process, so a really significant increase in the bending fatigue strength. The other three processes actually produced very similar results, despite the fact that we saw slightly different residual stress profiles. So they were between 61 and 64% uplift in bending fatigue strength. I think again here, there is a reflection in the fact that there is some difference in the duplex process. So in the finite life region, we do see some small increase in life for any given bending fatigue, root bending strength, stress, sorry. So overall, the condition cut wire process gave us the greatest uplift. So some fracture faces from these results. The S220 and the S230 and S330 gave us results as we would expect, as did the duplex process, and we consistently saw subsurface initiated fractures from inclusions in the steel. Two examples here, I think this is the 230 and this is the 330, but they were all broadly the same. I'm just trying to show you two good examples. For example, from a manganese sulfide inclusion, or I think this is aluminium oxide cluster. There's some manganese sulfide included in there as well, and these tend to form in clusters. The baseline steel, as we would expect, consistently failed from surface-initiated fractures, and these were generally from intergranular oxidation, as I said, from the gas carburizing process. So finally, I think the one, again, of most interest is the condition cut wire process. All of these fracture faces that were analysed all showed surface-initiated fracture rather than subsurface-initiated fracture, which isn't what we would have expected for the shot peening process. The only caveat to that is that from the manufacturer that was involved, the condition cut wire gears and the baseline gears were certainly forged from the same batch. The others were taken from a different batch, so perhaps that gives us some reason for why that occurred. So some conclusions. We've looked at the bending fatigue strength of as carburized baseline steel and compared that to 4 shot peening processes. We've looked at some residual stress measurements, and we've shown that the condition cut wire gave us the greatest change in compressive residual stress over the broadest peak of minus 1,100 megapascals. The minimum uplift in bending fatigue strength was 61% from one of the standard shot peening processes. The greatest uplift is 86%. So we compare that back to what we discussed from ISO 6336, where they're suggesting to the gear designer that we see a 0 to 10% increase. Again, there is a bit of a side to that the ISO 6336 doesn't make it entirely clear what condition the material is. From our experience, it's actually as carburized and shot blasted. So shot blasting is used as a surface cleaning process. You do get some small compressive residual stress as well, but it does remove away that oxidized layer, and you generally see an increase of around 50% just from shot blasting. So if we use that as our baseline of 50%, then we see this 61 suddenly becomes 10%, which is what the standard suggests. However, the condition cut wire is still 36% above what we might expect for that, so it's very promising. Future work, we would suggest we'd be looking at additional optimization of condition cut wire processes. Again, in this package of work, we didn't look at surface roughness, so there may well be some surface roughness effects. However, previous work, and I can find paper references if people are interested, did look at surface roughness and bending fatigue failures. However, they were comparing them across different media processes. So again, perhaps there's maybe something to look at with the same condition of wire or shock peening process, and then trying to establish a secondary process, maybe a duplex process, to change the surface radius parameters, which isolates some of those different effects from the other shock peening processes. So thank you very much for your attention, and excellent.